All right. Our station is called gas station because we're using gases. Okay, and then the people have a hard time, at least in my experience, understand why we call ourselves gas man, gas woman. Do you have any? You probably already know. Why is a gas man a gas woman? Why we like to use a gas?
It's usually how we provide anesthesia.
It's not. It's not what you tell to do and you will do. Bigger? No. The gas man really would take a benefit of the pharmacokinetics. Pharmacokinetics. Body kicks foreign body out of the system. Okay. The we have experienced sometimes inject some medications too much or wrong medications. What are you guys gonna do? Uh-oh, that's it, right? With the gas, you can get in, you can pulse out, you can make a concentration steady. Right? Agreed. That's why we wish all the medication we have in the medicine drawer are all gases. But unfortunately, it does not happen. We only have a couple of those. Okay? That's why propofol running for a while, and then we still have not completely switched to propofol. That's one of the reasons. So today this operation is a very like a black box kind of situation. So we just turn on and off. We really don't know how it works. So we invited our senior scientist from Argonne Laboratory, Dr. Lu, and full professor at the University of Chicago, to give us a talk about the basic of physics about this vaporization. Okay, then we're going to addressing the certain things we talking about it related to vaporizing in terms of a clinical usage and what kind of problems we have. Okay, please.
Hi, I'm Zhentian Liu. I'm a physicist, and this is my first day ever talking physics in a hospital, so I'm very excited. I told my students, I said, I'm going to hospital to talk about physics on Saturday. One smart guy pointed out that that's quite fitting because he said, you too put students to sleep. And so Dr. Hu asked me to come and talk about evaporation, about temperature and pressure. I think it's the easier way to understand it all is if you have a molecular picture of the state of matter. Okay? So the solid, liquid, and the gas. In solid, all the molecules are down very tightly with each other. No molecules can get out of position. Okay? That doesn't mean the molecules are standing still. They're actually jiggling and shaking quite violently in its place. Okay? And we all intuitively know, because you can feel it. You can feel the temperature of the material. Maybe you can come closer a little bit. Yeah, because there are other people talking also. Yeah. So when we feel it, we can feel the molecular motion. So you have a piece of solid, you touch it, and if the molecular motion is vigorous, then it feels hot. Okay? And if it's less so, then it feels cold. That's all. That's what temperature is. Okay? And as temperature rises, eventually the shaking is so hard that some of the molecules start to pass from each other. Okay? That's when solid melts into liquid. In the liquid, molecules are still tightly packed, but they can pass each other. Okay? They can flow. Okay? And if you increase the temperature even further, eventually some of the molecules will pick up enough energy to jump off the liquid surface, and then they start to fly around with lots of space between them, and that's gas phase. Okay? In the gas phase, there's a lot of space between the molecules, so then the gas is compressible. You can push it down, and it will shrink, expand, right? Not in liquid. In liquid, it's tightly packed, so you can't quite compress and change its volume. Okay? And if you increase the temperature even further, the vapor pressure will eventually rise to match the atmospheric pressure. And when the matching happens, what happens? Something dramatic happens. So when the vapor pressure of a substance equals atmospheric pressure, it boils, right? So, if you heat the water to 100 degrees C, you start to see bubble form. That's the extreme type of evaporation. Okay? Boiling very much depends on atmospheric pressure. The atmospheric pressure changes from location to location. It's determined by how much air we have above us. There are a couple of miles of air above us, and all the burden is upon us. Okay? So if you move to a higher ground, say you move to Denver, Colorado, it's a mile high, there's less air above you, then the atmospheric pressure drops. But even actually, if you take an elevator ride up the Hancock Tower, the atmospheric pressure drops also. For every 100 meters of rise in altitude, the pressure drops for about 1%. And you can feel it. Right? Sometimes you can feel the ear as the airplane goes up and down. Right? Dr. Hu tells me that it affects how the instrument performs also, because you're flowing some carrier gas to carry the medicine into the patient. The amount of the partial pressure of the medicine is determined by the temperature of the evaporator, right? But if the atmospheric pressure drops, then you have less carrier gas to carry it in, so the concentration of the medicine is now higher. So then in that way, you have to make some adjustment if the pressure drops or rises. Even at the same location, at different days, the atmospheric pressure changes. Could be on the percent level. You heard on the radio that there's a high pressure front moving in, right? Different weather patterns can change the atmospheric pressure. Okay? So we talked about temperature, atmospheric pressure, the vapor pressure, which is determined by the substance. Different molecules can have different vapor pressures at the same temperature. So that's why these machines are designed for specific substance. Okay? Certainly, you know that alcohol is much easier to evaporate at room temperature than water, because the alcohol molecules don't bind to each other as tight as water molecules. Okay? And the vapor pressure rises quite dramatically with temperature. It's not a linear, gentle rise. It's actually exponential rise. Okay, so regulation of the temperature is actually very important. The other thing you may have noticed is as things evaporate, it carries energy away. Because it takes some energy to take this molecule away from the surface into the gas phase. Okay? So as molecules jump off the surface, it takes energy away, leaving the liquid colder than before. That's why in the morning when we step out of the shower, we feel cold, because the water evaporation carries heat from your body. Okay? And so the modern machine, I understand from Dr. Hu, actually temperature regulate, just to prevent this problem. Okay? Temperature is very important in vapor pressure and eventually in the concentration of the medicine. Okay? That's all I want to say.
Okay, good. So basic science over there. So we're now talking about we're gonna use it clinically. Okay. So vaporization using clinically, we have achieved two things. You have to achieve the two things, otherwise you cannot do it. One is called consistent concentration. I want 1%, it will be 1%. I want 2%, it will be 2%. Makes sense, right? Okay. The other one you want to achieve is adjustable. You want 1%, later on you want 2%, later on you want 0%, it's adjustable, right? And if you can achieve those two, then we are good shape. Temperature, Dr. Lula talked about it. Pressure, Dr. Lula talked about it. So we are now working on the really close chamber. We actually need using the vaporized gas to the patient, right? So we have to have some carry on, we call fresh gas flow, to get in, get out. This is how we get in temperature, right? Okay. So we talk about three things, right? Focus on those three things and introduce all those mechanisms, all those vapors, and see how they actually achieve those things. Two goals, three things try to compensate, not impact on the concentration. Talk about the temperature first, since we already addressed the temperature. Temperature has a lot to do with this business, okay? We already understand you want to liquid the vapor, you have to have a consuming energy. This energy is temperature. So let's say you have hooked up with the flow, gets in, gets out, so you blow all the vapors. So you need to actually have more vapors to come in, right? If you don't have more vapors come in, obviously you cannot achieve consistent concentration. Clear. So then, because of your vaporization is causing your energy, causing your temperature is going to go down. To a certain point that you're not vaporizing anymore. So how we actually take care of this business. Okay. So there's a called vapor chambers, okay, which is a little bit Cooper looking, okay, the brown one inside of it. And this wall is very thermal conductive. Okay, so you will suck the room temperature in there to make this vapor keep going. That's how we actually take care of the vaporizing, the temperature cost, energy cost. Clear? Secondly, the temperature. Everybody knows the our vaporizer has to be agent specific, right? Everybody agree, right? Why?
Because they have different pressures. They go in
Vapor pressures. They have a different vapor pressure. So vapor pressure, why we need a different containers?
Different, well, they are constructed differently to provide the pressures, or they
What is very good point. Constructed differently. What is the part of their construction actually related to this issue?
the size of the machine.
No.
The temperature at which the heater goes to is definitely something that changes. Or machine, whatever is the element that will warm the liquid agent is something that will be device specific, I think.
Okay. Almost there. Anything else? Add on? So there's a one gate. Opens up, close up, smaller, little, get it bigger, smaller. It's called, what is the name called?
Bimetallic valve.
Bimetallic valves. It's a valve, basically like a gate. It's sensitive, high sensitive to temperature. Because the vapor pressure difference on the agent, right? So they actually causing different the energy to vaporize it. So then they're actually changing the temperature. So in order to make the temperature consistent, the concentration consistent, they changing the temperature will change the gate of valve getting either bigger or smaller. Okay, just imagine we walk on here. Obviously, we have a one temperature. We walk on outside is a different temperature, right? And we want the temperature always not impact on this vaporization. We call temperature compensation. Okay, so this would happen. Okay, so it has to be vapor specific. In the old days, this is how we actually fill up the gas. Opens up, pour the liquids over there, close up. You can put everything over there. Waters, gasolines, all that, all right? So that's why we call incorrect agent, okay? So there's a question in quiz. You probably already got it, and then we'll have another one to come. So in the quiz, we'll talk about the pouring the wrong gas in those vaporizers. So what is going to happen is, let's say this is I believe you truly believe this is a halogen vapors. Okay, so it opens up. You put an isofolate on it. What is going to happen? It will be too much, overdose, underdose, or not change. 3 options. Not matters. Okay, I'll get you hints. Vapor pressure is those are 2 highlighted one. Halogen and isofolate.
A little bit less.
Okay. So this is a question going to show up over there that trick you. Even we don't use a halogen anymore. The tricky is it doesn't matter because they are so close. Okay. But you just imagine if you put the gas flowing in this chamber, then what happens?
Dust and halogen?
Yeah. You overdose or underdose? What's that? You overdose. Okay? Obviously, you only have a 50% right or wrong, right? Over and under. So this is how we actually remember. You high vapor pressures, you put them in low vapors, and then you actually sense the temperature will regularly different as we already talked about. And then you actually vaporize more, you have a less dilution, you have a high concentration, so you overdose. Okay. H, L, H. So high vapor pressure, put them in a low vapor, and will higher dose. Okay. So this is how it, and then the other way around. Okay. So this is why we need a vapor specific, okay, agent specific. So we're talking about just back to the track. We're talking about the temperature business. We talk about the agent specific. Okay. There's another temperature business that we related to all the vaporization of vapor we used over here is that's for. Okay. Anybody touch the vaporize when you operate on paper? This is a one, no doubt about it. What about those? You don't feel different? A little cool, but not that much. But this is for sure. People all understand this is heated. So we look at the vapor pressure, right? Oh, forget about vapor pressure. Well, let's say vapor, the point, the point. Okay, it's at 23.5. It's about room temperature. So in other words, when you're cooking, boiling, that's flowing, right? This time. So we heat it more. The reason we have this issue is because at the room temperature, you already have an over vaporizer. Remember, we have to have the control, right? If this keep a vaporizer, then you probably get 1 millimeters of vapors. You have to have 1,000, like 100 liters a minute, like a minute of the fresh gas flow to dilute it in order to medically use. Otherwise, you can overdose later, right? So this is not adjustable, but this is a good one. We want to use it, and then we have some technology to use it. So we make it short. The reason we already understand you go boiling water here is at 100 degrees. When you go to Colorado, will be how much? It will be less, right? Maybe 80 degrees or I'm just saying words. Maybe 95 degrees, maybe more close. They start boiling. Okay. So what? So in other words, if we get dig a bigger holes in the earth, you got the other side of Colorado. Okay, and then the boiling temperature will be higher. Okay, so we just time 2, we just roughly maybe 200 in the 2 atmosphere. Now we have a 1 atmosphere, right? We have 2 atmosphere, the boiling point will be 200. Okay, understand, still follow? Okay, so when they actually changing on this, the atmospheric pressure goes high and double, and this is actually cut by half. Okay, so that become inoperable. It's operable, right? Because if we cut by half, it will be 303 something, right? So it's workable, right? So you can adjust it. This is what we actually do, why we heat it. Okay, so it becomes adjustable. So that's the temperature. Then we'll talk about the pressures. And pressures only have usually doesn't impact anything in terms of concentration. But I only have one thing that changes because the temperature changes. That's flowing good. So that's flowing heated. Remember, boiling point is different from Denver's and here. Okay. So over there you have generally the different atmospheric pressures. Instead of two, you probably have a different. Okay. Then you have a different boiling pressures, and you generate different pressures. So your pressure is changing. So that's why they say there will be an underdose if you go to Colorado. You have to increase the concentration in order to achieve the same amount of chemical effect. Okay, so that's the only one you need to sort of work on. Okay, the pressure. So pressures are easy. And then I will talk about the third part, flow, in and out. Because without the flow, we cannot use the gas, right? So we gotta get to use the flow. Remember that gate, close and open the gate, has a certain compensation in terms of flow, fresh gas flow rate. You talk about a range of 250 millimeters per minute to 15 liters per minute. Okay, what is the concept of 15 liters per minute? What is the fresh gas flow and the oxygen? How high you can actually run? 10 on the mark, right? You're able to go up to 15, just 5 liters at height. Okay, but if you're running two, like air plus oxygen, then you double, right? So when you doubled, you overfloating, you vaporize, you have a certain amount, but it flows really high, so you actually carry less concentrated vapor. Understand? Right? So you only have a certain amount of vapors to vaporize, and you cast big wings and blow it away. That's what it's doing. And then that's a flow too much, and a flow too low is usually not an issue. But back to 1995, this Vaporizers business, they have to have a minimum flow of 2 liters, not only for the scavenging business, the absorbent business, also you have to vaporize it. So there's the reason is, you look at all the numbers, this is the lowest. That's why you need a relatively high flow to achieve the vaporization. So that's one thing, okay? Adjustable, right? We have to justify in order to use it. So we'll look at justify. You have a couple different kind of method to get a gas concentration. There's an old one, we no longer use it. It's called bubbling. We're still using part of it. So gas, the tubes underneath of the fresh gas flow is underneath the liquid, basically. When you bubble it, it's just bubbling. Okay? It's 100% go in. But the problem is that you cannot get a control of. So then we call variable bypass. This is very typical. All our vaporize, it works this way. Okay? So variable means you can justify by this bypass chamber. 20% go over there bubbling, still bubble, and then go over there and then dilute it with the fresh gas flow and achieve certain concentration. Okay? And then when this also called bypass, also called variable bypass, but the bypass, when you do the liquid chambers, they don't actually go inside of a liquid. They actually go over, right? So that's called flow over. Instead of bubbling, that's a flow. That's what the difference is between the two. They both call variable bypass. Okay. There's a one, the other one, third one, is called the dual circular system. So the gas goes to gas, fresh gas goes to the fresh gas. They mixed up with the heat over there. So there's a one, somebody called injector, somebody called gas blender. It's a way you can imagine when you get in the door today. And the security probably hate to actually put a disabled door wide open. Cool air blows in if you're cold. Right? Inevitable. But if you go to the nicely go down blending door, you probably carry less gases, okay, less cool weather. So remember, we have even with two atmosphere, you still have a very high vapor pressures in the gas flow, right? Remember that? So that's why they actually get the gradually period of time, rounds and rounds, and this is how it works. Okay? So they actually mixed up with this. Alright? So when you talk about too much flow, too less flow, you talk about the vapors, all that, and there's one issue, there's two issues. You get a wrong circulation. It happens. One circulation called pumping effect. You heard of that? Well, you don't know what it is. You guys know, anybody know pumping effect? Pumping effect is when you actually generate the pressure backwards. Okay? When is it going to happen? Fresh gas, the oxygen, that blue bucket, the green bucket. You generate positive pressure, or patient bucket. Okay? Then the things come back. This has no protection. So the machine has a protection. They have a checkoff valve. Physically, you will see that station parts of service. But checkoff valve only have a one-way valve. This is how they actually get protected, not pulled back. Also, the people make a vapor chambers, bypass chambers smaller, so you don't get that much, right? They also nail down this, so create a more resistance, so you don't get too much to the system. That's how we actually take care. Okay. And those, you see this restrictor? You see this guy? They have two restrictors on there. They are protecting from pumping. So they don't have. The reason we need to do negative pressure checking is we need negative checking on the list. FDA provided that every machine has to do it, just because of this issue. And there's another wrong way to do it with the tip. 45 degrees changes. This thing is going to go backwards. Okay, and then this is also going to go backwards. This is better. Okay, we're going to have a handout, and then you guys have details about all those things. Okay, and this is a high tech because there's no chamber. Only have a one chamber, so it's 2,000.